All right, well, good morning. Welcome to another lovely Monday here in calculus. Um, so the plan today is to basically pick up where we left off before the exam. We're going to keep looking at applications of the derivative, and specifically today we're going to be talking about extrema, maximum and minimum values, and also address some theorems that we're going to use that relate to the derivative. So that's the plan. But of course, before we do that, I'm going to open it up to you guys. Any questions about the homework or anything else we've been talking about?
I had a question on 4.2, but I forgot what number it is. It's the sphere problem.
Um,
The circumference of a sphere is something centimeters, and then the error is off by this 0.5 centimeters.
okay.
And then finding the max error and then the relative error. I think it's 6 or 7. It should be
Okay.
6 or 7 on 4.2 if I'm not
We'll,
wrong.
we'll be able to find that. Okay. So, and then I see in the chat box we've got 4.2 number 8 and 4.1 number 1. All right. Any others? All right. Well, if anything else pops up as we're going, just let me know. But I'm going to go ahead and share my screen here and we'll go find it. All right. So hopefully everybody can see. But let's go check out the related rates question. All right. So good old just question number 1 from 4.1. So it says we want to find dx dt at x equals 4 if y is equal to negative x squared minus 5 and dy dt is equal to 5. Okay, so let me just write this stuff down. Okay, so this one, since we're looking for dx dt, we're going to want to differentiate with respect to t. So this is implicit differentiation. We just have to make sure that we implicitly differentiate each side of this equation. And then we'll just put in the values that we're given and see what we find. All right, so let me go to a whiteboard here. All right, so we were given y equals negative x squared minus 5. And we want dx dt. So since we want dx dt, we're going to go ahead and do a ddt of both sides. All right, so now y, since y is a function of t, its derivative is going to be dy dt. On the other side, minus x squared would give us minus 2x. But since we're differentiating with respect to t, and x is assumed to be a function of t, that means we have to throw on a dx dt for implicit differentiation. And then the minus 5, its derivative is 0. All right, so when we're doing related rates questions, when we're differentiating with respect to something that's not y or x, we just have to make sure we use the chain rule on each one of them, put on their respective derivatives. Okay, so here's our derivative. I'm going to go ahead and solve it for dx dt, just divide by the minus 2x. So we've got dx dt is equal to negative 1 over 2x times dy dt. And now we can put in the information we were told. We wanted to find this rate of change when x was equal to 4. And we were told that dy dt was equal to 5. Okay, so 2 times 4, of course, is 8. So we get minus 5/8. So there is our answer. Now, what this tells me is that x is decreasing at this point in time, right? When we're here, dx dt is negative 5/8, so it's a decreasing quantity, which would matter if we are actually using this for some sort of an application. But since this was just, hey, find a value, there's our value. All right, so how's that for number 1? I forget who asked for that one, but all right, looks good. All right, cool, there it is. All right, so there's 4.1, number 1. So let's go back to the homework set here, and let's go find the one from 4.2. Okay, so let's back up here. That's fine, don't care about my grade. All right, so any good, bad jokes for this morning while we're waiting?
Why do golfers wear 2 pairs of pants?
Oh, hold on. Why do golfers wear 2 pairs of pants? I don't know, Susanna. Why do golfers wear 2 pairs of pants?
In case they get a hole in one.
Ba-dum-bum. Nice. And that's exactly what I mean by a good, bad joke. So thank you for that. I'll have to remember that one. And you could make all kinds of good variations on that too. Why do golfers always carry around an extra sock? Why do golfers always carry 2 umbrellas? Well, it's good to see that my computer's feeling like I'm feeling. I'm super tired this morning. I'm going to go on record here and say I officially hate time changes, and it doesn't matter which direction they go. They suck regardless. All right, so here's number 8. So it says let y equal 4x squared. So find the change in y, delta y, when x is equal to 4 and delta x equals 0.1. And then it says find the differential dy when x is equal to 4 and little dx is equal to 0.1. Okay, so this one, we're actually trying to find these 2 things, and I'm going to guess, and maybe I shouldn't put words here, but I'm going to guess, because Bailey was the one that asked this, that maybe the question is, which is which? What's the difference between a delta y and a dy?
Yeah, that's exactly what my problem was.
Okay, that's kind of what I figured. All right, well, let's go back to the whiteboard, and because I just wrote down all the information there. And let me show you what we're talking about, like what's what. Okay, so remember when we've got some sort of a function and we're looking at a point and we find the tangent line at that point. what we're doing is we're taking a step away. And so for both of these, this horizontal is going to be delta x, and it's also equal to dx in the context of the differential versus the not. But now there are two different kind of y pieces. There's this one that's I'm going to make green that just goes to the function. And then I'll make another one. Let's make it say pink. That goes all the way up to the line. So the one on the tangent line, that's our differential. That's our dy. The one that's the actual change in our function value is the delta y. Okay, so that's what the two different things are, the delta x, delta y versus the dy and the dx. And really the idea is that if delta x or dx is small, then delta y and dy look pretty much the same. Okay, so here's what we're going to be doing for this specific problem. So we had y equals 4x squared. We were told we're at x equals 4, and then delta x was equal to 0.01, just 0.1. And then we're using the same dx either way. Okay, so let's first think about the function difference. So delta y, that's going to be f of 4.1 minus f of 4. Okay, the way that this is playing out, this is 4. This is 4.1. Right, we're told x equals 4 and delta x or dx is 0.1. So the actual change in the function value is going to be given by this. So this is going to be 4 times 4.1 squared minus 4 times 4 squared, which is whatever number that happens to be. I don't really care at this point. Okay, so that's how we can find the actual change in the function value. Now, if we're going to use, or if we want to find out where we are on the line, that's where we need to use the derivative. And so we know that dy is going to equal f prime of c times dx. Just think of it dy dx as a fraction. We multiply that over there. So in this case, the derivative is 8x. So dy is going to be 8 times 4, because that's where we are, times dx, which is 0.1. And so dy is 3.2. Even here, notice that dy was way easier to find. Like I was able to actually calculate that without too much trouble. This one I still got to think a little bit. Oh, I got my calculator here. Hold on, I'll get that number. So we have 4 times 4.1 squared minus 64, which is 3.24. So notice that these two numbers are very similar. That was our dy, so that's what our guess is using the tangent line. This is the actual change. And really the point of this problem is to show you that those two numbers are not very far off because we're taking a tiny step. And the smaller the step, the closer these two numbers are going to get. All right, so cool for that one, Bailey? Yeah. All right. Awesome. Okay, well, I'll tell you what to do. Let's see if we can go find the question that Susanna had about the sphere. Let's see. It doesn't look like much like a sphere. All right, so this one could be the one if it, depending on how they give variations.
If I'm not wrong, it's 7 or 8. Or
Here, I think this is probably it.
yeah,
Number
I think that's
6.
6. Okay.
Okay, so let's take a look at this one. So it says we have circumference of a sphere is measured to be 70 centimeters with a possible error of 0.5 centimeters. Okay, so we're plus or minus 0.5. That's cool. Use linear approximation to estimate the maximum error in the calculated surface area. Okay, and then says estimate the relative error. So we want to find both the error and the relative error with this plus or minus 0.5 centimeters. All right, well, there's all the information. So we got that. Let us go to a whiteboard. All right, so we've got a sphere. And we know that its circumference was 70 plus or minus 0.5 centimeters. All right, and then we want to find the error in the surface area. All right, so where do you think we should start here? Any ideas?
Isn't C equal to pi d or pi r squared? And then
Okay.
differentiate.
Okay, so a couple pieces in there. So Susanna, you're trying to get me an equation. So let's just generalize it to. We got to get an equation for the thing that we're curious about. So in this case, surface area. And then once we have that equation, we do want to differentiate. But let's just start with surface area. So for a sphere, the surface area, I don't know if anybody knows this formula, but it's 4 pi r squared. Okay, so you can look that up, right? Do a quick Google search or something, and you'll see surface area is 4 pi r squared. Now, if I just differentiate this right now, I will get my dA, right? dA delta A error. But the problem is it's going to be in terms of an error in the radius. And I don't know the radius. What I actually know is the circumference. So what I'd rather do is get this equation, my surface area equation, in terms of circumference. So we're going to do this by using the formula for circumference. And hopefully you guys remember circumference of a circle is C is equal to 2 pi r. So r is actually equal to C over 2 pi. And we can take this, put it into our surface area formula so that we can get it all in terms of just circumference. So the area is going to be 4 pi times C over 2 pi squared. And that's going to simplify to A equals C squared over pi. The 2 squared becomes a 4 that cancels with that 4. And then the pi squared on the bottom cancels with one of the pi's on top. So when you find the equation, when you look for an equation, you want to make sure that that equation has both of the things in it, the what we're trying to measure and what we already know about. Okay. So if I differentiate now, I'm going to get my dA is equal to 2c over pi times dc. Actually, let me just back up. We get a dA dc. I differentiate with respect to c. So dA dc is equal to 2c over pi. But if I'm just looking for dA, it's equal to 2c over pi dc. So now I can actually figure out what that error is. So the dA is my error in my area. I need to know C and DC. So I need to know the circumference. Well, I know that one's 70. And then I need my DC. And DC is the error in my circumference, which is the 0.5. So this is equal to 70 over pi, which is equal to some number slightly bigger than 20. Okay, so there's the error, potential error in the measure of the surface area of the sphere. So before we go and we find the relative error, is that okay? Any questions on that part?
Bruce?
Yes.
What'd you do with the 2 and the 0.5?
Just multiplied them together.
And it, okay.
2 times 0.5 is equal to 1.
Okay. Thank you.
Yeah, you're welcome. All right, so there's our error. So now if we want the relative error, to get the relative error, we're going to take our error and divide by the actual amount. So we're going to take that 70 over pi, and we're going to divide it by the actual surface area, which is going to be 70 squared over pi. Where that 70 squared over pi came from was back over here. The area is equal to c squared over pi. There's my c squared over pi. So if I invert and multiply, this ends up being 1 over 70. Let me go ahead and get a decimal for that. That's 0.014286, whatever. So this is around 1.4%. So the relative error, so this gives us an idea of how bad this error actually is. It's a 1.4% error, which isn't terrible, right? In fact, in the science world, I promise you, if you ever do anything in lab and you're within 1.4%, you are going to be super ecstatic, because that's a really, really good number. All right, so there's then the relative error. So that's the difference between the error and relative error, but hopefully that helps out a little bit. Is that Susanna who asked for this one? Is that good?
Yes,
Feel
thank
better?
you.
Yeah, you're welcome. Let me just show you something else that you can do with this. Is kind of cool. If you want to figure out the relative error it turns out that the relative error, it's always related to the relative error in the other quantity. So in this case, the circumference. Because check this out. Let me, where do I want to go? I'm going to erase. No, I want that DA. No, erase up here. I don't need this anymore. Okay, because check out this. If we want to find the relative error, that's dA over A. And we have formulas for both of those. The dA, that's 2c dc over pi. Okay, that was this guy right here. And then we're going to divide by the area, which was c squared over pi. So you can cancel some stuff out. The pi's go away, one of the c's go away, and you're left with 2 times dc over c. So this, the pink one, is our relative error in the area, the surface area. The dc over c, this blue one, this is the relative error in the circumference measurement. And so notice that the area relative error is twice the relative error of the circumference. So we actually could have answered the second part without calculating the actual error in the area. What we could have done is just gone back to the error in the circumference. I erased those numbers up here, but that was, we were off by 0.5 centimeters over the original 70. If we had fired that in there and then doubled it, 2 times 0.5 becomes 1. We get 1 over 70. Boom. And there it is. So if you don't want to know the actual error, if all you want is relative error, it can be faster if you do this. Just a little advice from Bruce to you, someone who's done a bajillion of these to someone who hasn't. This can be a time saver. All right, so was that pretty much what you were looking for, Susanna? We good?
Yeah, it was more detailed. Thank you.
Well, that's what I do, right? All right, cool. So anything else from homework? Or any other questions on this one? All right, well, hearing none, I'm then going to go ahead and hop up to the whiteboard, and I will see you guys in just 1 second. All right. So we're going to continue our discussion of things that we can use the derivative for. And like I said, the first thing I want to talk about today are what we call extrema. I think sometimes people call them extrema as well, but I will say extrema. But extrema, all these are maximum and minimum values. So think about if I give you a function and I just want to know what is the biggest value that that function takes on. That's an extreme point. What's the smallest value that that function takes on? That's a minimum. That's also an extreme point. So this is really what we're going to be talking about, is given an equation, given a function, how can we use derivatives to help us figure out where extrema are located, or even better, are there extrema? Are there maximums? Are there minimums? Let me give you some examples of functions that have extrema and those that don't, because in your experience with lots of different functions, you've seen lots of different cases of these. So an example of one that has some kind of extrema would be, say, cosine of x. So think about y equals cosine of x. Is there a maximum value that cosine takes on?
The amplitude be 1.
Okay, so think about the amplitude does sort of tell us the range that we go through. But for y equals cosine of x, there is a maximum, and the maximum is 1. That is the biggest value that we get with cosine. How about minimum value?
-1.
There you go. Okay, so y equals cosine of x is a function that does have both a maximum and a minimum value. There's a biggest and there is a smallest, right? And so there's an example of one that has both, but you don't have to have both. Here's another one. What if I told you, how about y equals x squared? So think about y equals x squared, your good old happy parabola. Does it have a maximum value? Is there a biggest number you get with x squared? All right, thanks, Aries. It's infinite, right? It goes forever. So there is no biggest number, because any number you can think of, there's going to be something bigger than it. All right, so I'm going to put here that there is no maximum. Is there a minimum value? Is there a lowest, smallest value on that? Yeah, it's 0. So here's an example of a function that has one of them, but not both. Okay, so that happens. It's also possible to not have any. And a good example of that one is just good old y equals e to the x. There is no maximum because it grows forever, right? Think about e to the x as you put in bigger and bigger x's, it grows forever. And it also turns out that there's no minimum. Now, this one you may not be super thrilled about, though, because some people will say, no, there's definitely a minimum value for e to the x. What number is that? What number could you see people might think is the minimum value for e to the x? Think about its graph as you go towards negative infinity. What happens to these numbers when we put in really, really big negatives? Okay, cool. Thanks, Eric. They definitely do approach 0. So some people would say, well, there's a minimum here. There's a smallest value, which is 0. But the thing is that e to the x never actually takes on the value of 0. And no matter how small you think that number is, there's always a number smaller than it, closer to 0. Okay, so sometimes we'll have both. Sometimes we'll only have one. Sometimes we won't have either of them. And so what we want to be able to do is figure out a way to determine what situation are we in. Okay, but have no fear. We have something that's going to help us. Give me 1 second here. I'm going to see how the outside light. Oh, yeah, that's a problem. Never mind. I was going to try to keep my shadow off the board, but the way the sun is right now, it's going to really destroy everything. Anyway, all right, so how do we know which situation we're in and so on? Okay, well, let me give you some more terminology, and then I'm going to give you a theorem that's going to help us with this. Okay, so first of all, there's another classification with extrema. We have what are called absolute extrema, and we have relative extrema. So we definitely need to know the difference between those two. All right, so relative extrema, absolute extrema, what do these mean? Okay, so an absolute max, okay, I'm going to put it here, we say x equals c gives an absolute maximum if f of c is greater than or equal to f of x for all x. But that should make sense, right? Absolute maximum. It is the largest value that you can get. Okay, so f of c is greater than or equal to f of x, no matter what x is. It's important to notice the or equal, right? It doesn't mean that no other points give us the same value. It's just saying that there is no other value bigger than that. So come back to like cosine. This maximum of 1, right? That happens a lot. It happens at 0, 2 pi, 4 pi, 6 pi, 8 pi, at all the even pi's. So it's still an absolute maximum though, right? 1 is an absolute maximum because there is no other y value that we ever get that's bigger than that. And if you wanted to change this to minimum, so if instead of maximum, we'll put minimum here, the only difference for a minimum is you turn the inequality around. So we say f of c is less than or equal to f of x for all x. And the same thing happens with a min. It can be more than once that you get the same minimum value. And just the absolute minimum is such that there isn't anything smaller than it. All right, so that's what it means to be absolute. Relative, slightly different. So we say x equals c gives a relative maximum if f of c is greater than or equal to f of x for all x in a, and I apologize for this real quick, but I'm going to get mathy on you, in a delta neighborhood around C. Don't worry, I will explain. But yeah, there's that horrible delta coming back again that you saw before. Okay, so first, what's a delta neighborhood? What does that actually mean? Well, a delta neighborhood, this just means we're looking at an interval. And in this case, the interval is going to be from C minus delta to C plus delta. So hopefully you remember delta is just a little small value, small distance that we go away from C. I think we did that with limits. It's the same kind of idea. We're just saying that we can create a little neighborhood. And neighborhood's actually a math term, by the way. That's not a Bruceism. When we talk about neighborhoods, that's what mathematicians call it. But this is just a small interval around C. But what we know is that locally, f of C is the biggest point, is the highest point. And you could do the same thing for, like before. If we want to make this a minimum, just change the direction of that inequality. But it still means it has to be locally. So relative extrema, they're also sometimes called local extrema. So you can have a local max or a local min. And it is exactly what it sounds like. It's a highest point in the general area. It may not be the highest point overall in the function, but it's the highest one locally. So let me draw you a picture, give you an example. It would be something like this. So think about this function. So this would be some sort of polynomial function. And it does not have an absolute maximum because this just keeps increasing forever. It also doesn't have an absolute minimum because this piece keeps coming down forever. However, it does have relative extrema. And here are some examples. So this point right here, this is a relative max. So it's not an absolute max because there are values that are bigger than it, but it's a local or relative max because locally, if you were to look just right around it, it is the highest point. All right, hold on a second here. I got to read what the question was. So, Erez, when you say, is this different from local? What do you mean this? Relative? Yeah, no, relative, local mean the same thing. Right, that's why I said a little bit ago, some people call these things local. Right? The two words, they're synonymous. Okay, so that's a relative maximum because everything right around it is down, is lower. Similarly, take this dot right here, I'll make a blue dot. This one's a relative or local min. Because it's a low spot locally, right? It is not the lowest point in this graph at all. There are other spots that are definitely below it. However, it's locally a minimum. Okay, so it's definitely possible that even if a function doesn't have absolute extrema, it can have relative or local extrema. This actually has a couple more. There's another relative max over here at this little mountaintop, and there's another relative min down in the bottom of this valley. So for those of us in Tahoe, this makes total sense. We know all about local extrema. Every time, anytime you've ever gone on top of one of the peaks, you're at a relative max. So you go hike Friel. You get to the top of Friel, there's nowhere to go but down. However, it's not an absolute max. There are places in the world that are taller than the top of Friel. Go to Whitney, for example. Right? Okay, go to the top of Talac. Again, nowhere to go but down. So you're at a relative max. However, that doesn't mean you're at an absolute max because there are other places that are taller than Talak. Take Friel, for example, right? So that's the difference between an absolute max and a relative max. If we're going to talk about mountains and highest points on Earth, then the top of Mount Everest would be the absolute max. You get up on top of there, there literally is nowhere to go but down. No other place on Earth is going to be that high, right? But you get on any other mountain peak, and that's a relative max. And then the same thing with mins, right? You get down into any kind of a valley, any kind of a bowl, and that's your local or relative min, right? So like Death Valley, I don't know if anybody's ever been to Death Valley, but you go to Death Valley, you get to that lowest spot that's like 240 some feet below sea level. That's a local minimum. There's nowhere to go but up. But it's not an absolute minimum because there are places on Earth that are lower than that. If you actually wanted to get to the absolute min on dry land, it would be at the Dead Sea, right? That would be your local minimum, or sorry, your absolute minimum. All right, so cool with the difference, hopefully. It kind of makes sense. Just think about there's nowhere to go but down. Locally, that's a maximum. Nowhere to go but up. Locally, that's a minimum. Okay, so now that we've got these, how do we know when they occur? Well, that's what we're going to use this thing called the extreme value theorem. So, extreme value theorem. And I'm going to abbreviate it EVT, not to be confused with the IVT, which was the intermediate value theorem. Don't know if you remember that guy. Intermediate value theorem was if we've got 2 points and a continuous function between those 2 points, then we get every value, every y value between those two y values. Yeah, maybe you remember that. Anyway, but here's the extreme value theorem. So first of all, this is what we need, is if f of x is continuous on an interval AB. So it doesn't necessarily have to be continuous over the entire real numbers, but we're just going to specify between A and B. Okay, so if f of x is continuous on AB, then there is an absolute max and an absolute min somewhere on the interval AB. Get my shadow out of the way. All right, so just look at what that's saying. So we have to have a continuous function. All right, well, we all know what that means, right? You can draw it without lifting up your pencil. Well, if that's all it is, if it's just continuous, then there's going to be an absolute max and an absolute min somewhere on that interval. So let me show you what we're talking about. So we'll do a whole bunch of different kinds of functions that are continuous from A to B. Okay, so here's some sort of a B. And all we need is a function that's continuous between A and B. All right, so let's start with, say, this one. So it is continuous between A and B. You saw me draw it without lifting the pencil. And looking at it, hopefully you can see an absolute max and an absolute min. The absolute max is right here. I'll use red for my max. And then there's an absolute min. I'll use blue for that. Down there. But there is a largest value and a smallest value somewhere on that interval. All right, so here's another one. Let me do another A to B. All right, so if we look at this one, again, there's an absolute max. It turns out it's this point that's over on the right. And there's also an absolute min. That's this point on the left. It also has a couple of relative extrema. Think about this point right here. That's a relative max or a local max. It's not the absolute because there's another place higher than it. And similarly, this is a relative min. It's not the absolute min because there's another guy lower than it. All right, but basically, no matter how you go from A to B, if it's continuous, you're guaranteed to find an absolute max and an absolute min somewhere in there. Now, I want to do this next example because this is one that a lot of people like to fight me about. Don't fight me about this one, but I understand why you want to do that. But let's just go with a constant function between A and B. So we got a horizontal line. Now the extreme value theorem says, so since it's continuous in this interval, that there has to be a maximum value in this interval, an absolute maximum. Also needs to be an absolute minimum. Okay, so some of you probably already going down that path of, yeah, no, there is no biggest value. There's no max, there's no peak. There's no minimum, right? There's no trough. But this is one where the absolute max and the absolute min are the same number. Let's just specify a value here. Let's just say that this is 3, just for the sake of having a number. Well, what I know then is that the absolute max is 3. And I also know that the absolute min is 3. So am I right that this doesn't feel good? This doesn't feel right. But go back and you look at the definition.
It doesn't feel right, but it would be nice on a test for sure. Because you wouldn't have to show any, like, prove any work.
Yeah, you just look at it and go, 3. But it doesn't feel right. But go back and look at the definition. And remember, for the absolute max, it said it had to be greater than or equal to every other function value. Or for the min, it had to be less than or equal to every function value. So think about this. 3, is every function value in this interval less than or equal to 3? Yeah, or equal. How about, is every function value in this interval greater than or equal to 3? Yeah, because of the or equal. And so by definition, that 3 is both the absolute max and the absolute min. So constant functions, you're not going to like them when it comes to this, but Susanna actually had a point. They're actually really easy when it comes to extrema, because with a constant function, max and min, same number. It's just what it is. Okay, but the extreme value theorem tells us what guarantees having extrema. We can have extrema on a closed interval if the function is continuous. Now, if the function's not continuous, you can see why we might not be able to have extrema. Think about some of the discontinuities. Right? So like, I don't know, how about an infinite discontinuity? An asymptote, right? If you've got a vertical asymptote, there isn't going to be a maximum value or a minimum value because you're going off towards plus or minus infinity. You could also have issues with holes, with dots, right? Like, actually, here, let me show you a couple where discontinuity doesn't hold. So I already talked about an infinite discontinuity, but let's say we're looking at the intervals, say from -1 to 1 on 1 over x. And so if you look at this one, there is no maximum value because it grows forever. There is no minimum value because it drops forever on this closed interval. But we weren't guaranteed it because this isn't continuous. Here's another discontinuity that leads to a problem. Think about one of those that had a jump, right? So like, let's say we've got this. Okay, so here is a function that's got a discontinuity, and let's specify a to b. So let's say that this is a and this is b. So if we just go from a to b, so eliminate all this other stuff, this one has an absolute min. The absolute min would be 0. Right? 0 is the lowest, smallest value that we get in here, but it doesn't have an absolute max. Because even if, let's say that this was, say, 2, 2 is not the maximum value because we never actually get 2. We can get as close to 2 as we want, but we don't actually get it. Remember, that's what the open circle means. So this is another place where we don't get the extreme values. Well, we got one of them, but we don't get both of them. But there's a discontinuity. So as long as we're continuous, we're guaranteed to have extrema. All right, so that's good to know. If you've got a discontinuous function, you got an interval that contains a discontinuity, you gotta back up and go, oh, well, maybe I don't have them. If it is continuous, then you know you got them, so you can go ahead and find them. All right, so this is really a test for, do you know they are there? So then once we know they're there, the next question is, how do we find them? Right? Okay, well, turns out that they're not that hard to find because there are only certain places where they can occur. All right, so I'm just going to put here, where can extrema occur? Okay, so the first place that we always need to check when we're looking for extrema is at the endpoints of the interval. It is possible that those absolute max and absolute min are at the endpoints. Look at my second example here. Right, this was one where we saw the absolute max and min were both at the endpoints. Another good example of that would be a line. Take your favorite non-horizontal line. So take a linear function that's not constant, whether it goes up or down, doesn't matter. But no matter how we were to cut an interval on a line, we'd see that the absolute max and min are at the endpoints. Okay, so where can they occur? At the endpoints. Always got to check endpoints. Okay, but it is also possible that they occur somewhere in the interval. And those other places where they might be are what we call critical points. Now, a critical point, what this means, one of two things can happen at a critical point. One is that the derivative is equal to 0, or the other is that the derivative does not exist. Okay, dne does not exist. So places where the derivative is 0 or non-existent are what we call critical points. Because critical points can lead to extrema. An important word there, can lead to extrema. They won't always lead to extrema, okay, but they can. So this is the other place where they might happen. So let's kind of talk about these two conditions and why those do what they do. Okay, so we've got derivative equaling 0 and derivative being undefined. So let's think about what it's going to look like when we have extrema. All right, so I'm just going to talk about this with like a local, but that's kind of what we're searching for. So think about a local max. So here would be a place with a local max. And think about the derivative on this function. So I'm going to use the tangent line, use my pen as a tangent line. And think about what happens to this tangent line when we're up at that top. Right? You see how it got flat? So we're going up, we got a positive slope, and then it turns flat, and then goes to negative slope. So remember, when it's horizontal, that's a slope of 0. So that's our derivative equaling 0. So if the derivative equals 0, there's the potential that it's an extreme. Now, this was for a max. For a min, you can probably picture the same thing, but happens going down. All right, so that's why we got to check if the derivative equals 0. But we also could get a max or a min with something like this. So think about like the absolute value function. There's a minimum down there. So again, think about the tangent line. So this one, the tangent line is this line. We get to that point, and then all of a sudden, there's a huge change in direction. But you guys remember from our discussion of differentiation that if there's a kink, there's a real sharp turn, then the derivative doesn't exist. Well, that's why we have to look for the derivative being non-existent. Okay, so those are possible turnaround points. Okay, so that's why we check critical points. But I need to warn you, that there are places where the derivative is equal to 0 and places where the derivative that does not exist that don't lead to turnaround points. Let me show you an example of both, okay? Think about this function right here. If you had your tangent line and you're looking at the slopes, we get to a point where it's flat, but then start going up again. So there is a point right here where the derivative is equal to 0. But notice that it is not ever going to be an extreme value. There's no way that's ever going to be a maximum or a minimum, because locally, no matter how big of a delta neighborhood you make, there are going to be some values that are higher than it and some that are lower. A great example, again, for those of us that live where we live, this would be like at a saddle on a ridge. Think about if you're, I don't know if anybody's ever gone hiking up like Friel, Job's Peak, Job's Sister area. But as you're going from one to the next, you kind of follow along a ridge. But when you're up there in one direction, you go down. In another direction, you go up. But it's still relatively flat at that spot. Okay, so that would be a critical point that doesn't lead to an extreme. So there's where the derivative equals 0. That's not enough to guarantee, but it's somewhere we have to look. And you can also have a derivative that's non-existent. That does kind of the same thing. Doesn't lead to an extreme. So this would be this point right here. That one, the derivative doesn't exist because we have a vertical tangent line. And a vertical tangent line doesn't necessarily lead to an extreme value. Because again, look locally, some places you can go up, some places you can go down. So this would be you're on a cliff face. You never want to be on one of these spots if you're out hiking. That's a bad place to be. Anyway, so just because they're critical points doesn't mean they will be extrema, but we have to consider them as a possibility. Okay, well, I mean, this is good. Turns out that there's not a lot that we actually have to check for. But these are places where we have to determine, do we have maxes or mins? Okay, so let me show you the process, okay, because it's not really that hard. It probably seems like it's really convoluted, but it's going to be really easy. We're going to take our function, we're going to differentiate it. We're going to look for these places. We'll find all of those. And then we're just going to compare them to the endpoints and figure out which one's biggest and which one's smallest. So let's start with something kind of easy. Let's say we've got f of x equals x cubed minus 3x squared. And we're going to look on the interval minus 2 to 2. So think about the extreme value theorem. Says that if the function is continuous on a closed interval, then we're guaranteed a max and a min. An absolute max and an absolute min. So we've got a closed interval, minus 2 to 2. Is f of x continuous on that interval? The answer to that should be a pretty fast yes, because polynomials are continuous everywhere. So this one's continuous on that interval. We know there's going to be an absolute max and an absolute min. All right, cool. So let's find them. So let's start by finding critical points. Okay, that should always be your first step. So for the critical points, we need the derivative. Well, f prime of x is 3x squared minus 6x. All right, now we need to look at two things. The one is where the derivative equals 0. And the other is, where is this derivative non-existent? Let's actually answer the second question first because it's easier here. This derivative, 3x squared minus 6x, always exists. There's not a number we can plug in there where we have any kind of a trouble at all. So I'm just going to put here none. Don't have to worry about that in this case, right? So there are no places where it doesn't exist, so those aren't going to be critical points. But then we also have the derivative equaling 0. Well, that is possible. So let's see where that happens. So we can actually solve this by factoring. Factor out of 3x. And so there are two places where the derivative of this equals 0. X equals 0 and x equals 2. All right, so those are the only places where we might have an absolute extrema other than the endpoints, right? So we just have to check both of these. All right, so here's what I'm going to do. I'm now going to just take all of these values and figure out what their y's are. Okay, so I'm just going to make a little t-chart here. So I'm going to start making this list by putting on the endpoints of my interval. -2 and 2. I always start with those because I always have to check them. So then I go to my critical points and I figure out which of those are in my interval. Well, 0 and 2 are both in my interval. So I need to check them. So I'm going to check 0. I also need to check 2, but 2 is already on my list. So I'm not going to redo it. Right? So I'm going to check these 3 places. These are the possible places where I might have extreme values. All right, so let's see what our y's are equal to in these various places. The 0 is easy. If I plug 0 into the original function, I get 0. Right? 0 cubed minus 3 times 0 squared. The 2, if I plug that in, 2 cubed is 8. 2 squared is 4. So 8 minus 3 times 4 is -4. That's what I get when I plug in 2. And when I plug in -2, I'm going to get -8 minus 12, which is -20. So that was just a matter of plugging that into fx. Okay, so my absolute extrema, I know, occur either at endpoints or critical points, which were these lists, or these values in this list. So here's all I got to do is look at these y values. Which one's the biggest and which one's the smallest? Well, -20 is the smallest. So this is my absolute minimum. If you were to draw this function between -2 and 2, you would see that the lowest point on that graph occurs at -2. All right, and then we come down here and we see 0 is the biggest value on that list. So this is our absolute max. So again, draw the graph of this thing between -2 and 2, and you'll see that the highest point on it occurs at the point 0, 0. So basically, it's just a matter at this point, once you figure out endpoints and critical points, calculate their y's. Biggest y, smallest y, those are your absolute max and your absolute min.
So the extrema can only be critical points or endpoints, right?
Yep. Those are the only places they can happen when you have continuous function. If you have a discontinuous function, it's a completely different story, and then weird stuff happens because you can have extreme values at discontinuities. But if we're going to be specifically looking at continuous functions, the only place they can occur is either critical points or endpoints. Yep. All right, so how about let's do one more. But let's do one more that's a little bit more difficult, because polynomials are great. Like, they're super easy. But the thing is that they're not always, they're not always. So how about we do this? Let's try this guy. Let's look at f of x equals x times the square root of 4 minus x And let's look on, say, -1 to 1. Nah, -1 to 3. Let's go -1. Okay, so first of all, closed interval, right? -1 to 3, we've got brackets on them, so we know it's a closed interval. Is this function continuous between -1 and 3? And now you're starting to think, maybe, maybe not. Okay, well, that's why we got to think about these things a little bit. The x piece out front is totally fine. It's not going to do anything. We don't have to worry about it. What we really have to worry about is the square root. So the square root of 4 minus x, what are potential problems with that? Or are there any problems? All right, so Bailey just said not on this interval. Yeah, and that's actually the perfect answer. There are problems with this function. If x's are bigger than 4, then we've got square roots of negative numbers, and that's bad news, right? But we're definitely not there on this interval. So on the interval -1 to 3, we are good. This thing is continuous, so everything is fine. All right, so let's find critical points. So we need to differentiate this thing. Uh-oh. That means that we have to use the quotient or the product rule. So we take the derivative of x, that's 1 times square root of 4 minus x. Then we add to it x times the derivative of 4 minus square root of 4 minus x. Well, that's going to require chain rule. We're going to get 1/2 times 4 minus x to the minus 1/2 times -1. Good. Okay, so that was product rule with chain rule in it. All right, now, remember back in the day, like even on this exam you just took on Friday, when I was like, yeah, you get me here, I give you 10 out of 10, everything's good. Well, those days are gone. Now we're going to have to do the algebra. Now we're going to have to simplify this stuff because we're going to need to look and see where's it equal 0, where is it undefined, and it's awfully hard to spot that when it's written like this. So now we're going to have to start doing the algebra. So let's start simplifying this. It's going to be the square root of 4 minus x minus x over 2 square roots of 4 minus x. And now I want to get a common denominator. So I'm going to multiply that first one by 2 square roots of 4 minus x on top and bottom. And then when I combine all this together, I get 8 minus 3x divided by 2 square roots of 4 minus x. So I know there was a lot of algebra in there. Go back, look at it later, convince yourself that that's where this goes, okay, because we don't have the time to spend on the algebra, but that is the same derivative. But there's a reason that I want it written like this, because it's going to be a lot easier to see where it's 0 or undefined. So again, our two options. The first was where it equals 0. When you have a fraction, the only way a fraction can equal 0 is if the top equals 0. So that's going to equal 0 at 8/3. So that's the one and only place where the derivative of this function is equal to 0. All right, the other option is where this is undefined. Well, when you have a fraction, where you want to look to see where it's undefined is the bottom. And see if that equals 0. That gives us x equals 4. So if you solve that thing for x, you get x equals 4. So there's another critical point, x equals 4. We also have an issue if we have numbers bigger than 4 because the square root doesn't exist. But we're not going to worry about those for a couple of reasons. One, they're not part of the domain anyway. But two, they're not in our interval. So, but those are our only other critical points. All right, so let's start making our list of values we want to check. So I'm going to start with the endpoints. So the endpoints of our interval are -1 and 3. So I'm going to check those. So then let's go to our critical points. I've got x equals 8/3. And then I have x equals 4. But you'll notice I didn't write x equals 4. Why am I not going to include that 4 in my values that I check? Anybody see why that's going to be the case? Yeah, perfect errors. It's not an interval. I'm only looking for numbers between -1 and 3. So any critical points that pop up that are not in that interval, we're just going to ignore them. Pretend that that never even happened because it's not in our interval. All right, so these are the numbers that we have to check. All right, so plugging them in. When I plug in -1, I get -√5. I get -1 times the square root of 4 minus -1. That's -√5. When I plug in 3, I get 3. Because I get 3 times the square root of 4 minus 3. Well, that's 3 times the square root of 1, which is 3. Okay, now the 8/3, I'm going to have to do a little bit of work on that one. 8/3, I'm going to get, let's see, 8/3 times the square root of 4 minus 8/3, which is 8/3 times the square root of 4/3, which is 16 over 3√3. So we have 16 over 3√3, whatever that happens to be. All right, so here are my 3 values. These are the only possibilities for extremes. So I need to find the smallest and the biggest one. Well, the smallest one is pretty clear. It's the -√5. So that's our min. So our lowest point is out at x equals -1. Okay, so then the question is, which of these is higher? Which of those is actually a bigger number? Yeah, that's a good question, huh? Which one of those is actually a bigger number? Well, √3 is around 1.7, plus or minus just a little bit. So 3 root 3s, that's going to be around 5.1. 5.1 times 3 is less than 16. So that means that this number is slightly bigger than 3. So it turns out that this then is actually our maximum value. Use a calculator. Please feel free to use a calculator. I just don't have one handy. But I know that this number is bigger than 3. All right, so our absolute max then is occurring at 8/3. We get this value, 16 over 3 root 3. So this is the largest value in this interval. The smallest value in this interval is the minus root 5. So even when the function's not as nice, right, it's not a polynomial, we can still do the same thing, differentiate it, find out where it's 0 and undefined, and test those points against the endpoint. But I knew I was going to have an absolute max and an absolute min because it was continuous on this closed interval. And that's what the extreme value theorem guarantees. All right, so questions on this one? What questions do you guys have that I can help with? Okay, so I'm hearing none. So we're going to go ahead and step to the next theorem that I want to show you. So this was the extreme value theorem. We have 2 more theorems that I need to show you. I'm only going to show you one of them today. But this one's called Rolle's theorem. I've also heard it called Rolle's theorem. It probably goes by lots of different names, or lots of different pronunciations, I should say. But I call it Rolle's theorem. I believe that this is named after a French mathematician, so it's probably more like Rolle's theorem or something like that. But I'm American, so I'm going to call it Rolle's theorem. All right, so Rolle's theorem. Here's basically how this guy works. All right, it says if f of x is continuous, on a closed interval AB, and f of A equals f of B, then, let's see. Oh, I need one more thing. So it's continuous on AB, I'm sorry. Differentiable on the open interval AB, and f of A equals f of B, then there is a C in the interval AB such that f prime of C equals 0. So I'll give you a second to write that down and then we'll talk about what that means. So f of x is continuous on AB. Okay, we know what that means. No big deal. The same kind of condition we had on the extreme value theorem. But now we also need the function to be differentiable on AB. All right, we didn't have that condition for the extreme value theorem, but now it means it's differentiable. So that means no kinks, no vertical tangent lines, nothing like that. It's just a nice smooth curve the entire way. And then we need f of A to equal f of B. Well, that just means that those 2 endpoints have the same value. and they have the same y value. Okay, so we got the same y value on the endpoints, and then it's nice, continuous, and differentiable in between. Okay, now Rolle's theorem says that if that is true, that all that stuff is true, then there is a point somewhere in AB where the derivative equals 0. Okay, so here's your proof. We're actually going to prove 3 different cases. Okay, so case number 1, this is going to be where there is some point where f of x is greater than f of a. Because again, think about what this is saying. We're drawing a graph here. I'll draw a graph. We've got f of a equals f of b. So here's a, here's b. But f of a equaling f of b means those things are at the same value. So the first case is going to be where there's some point that's above this. So I'll draw a little red dot. Okay, so at some place, there's a point that's above it. Case 2 is going to be there's some point down below it. The third case is going to be where there's never above or below, where it's actually constant. Okay, so here's case number 1. There's some point where the function's actually bigger than the endpoints. Okay, so here's how this proof is going to play out. Since this function's continuous, the extreme value theorem tells us that there's going to be an absolute max and an absolute min. Okay, so we are guaranteed an absolute max and an absolute min by the extreme value theorem. Right? It's continuous. So what we were just talking about, we know for sure that there's going to be an absolute max and an absolute min. Okay, let's talk about the absolute max. Because we know these absolutes have to occur at either the endpoints or critical points. Well, if there's a number greater than f of a, that means these endpoints cannot be the absolute max. Okay, so what we know then is that this absolute max cannot be at an endpoint. So it must be at a critical point. Those were our only options, right? Okay. So there's an absolute max somewhere in here. It's got to be at a critical point. Well, now we'll go to the fact that it's differentiable. So remember how we can get critical points? They can either be where the derivative is 0 or undefined. Well, the undefined can't happen because it's differentiable. So this critical point must have f prime of c equals 0 since it's differentiable. Okay, so there we did. We just proved case 1. Remember, what we're trying to show is that there has to be a place where the derivative is 0. And there it was. If there's a point above f of a, then the absolute max is not at an endpoint. Well, so at a critical point, then it's either the derivative is 0 or undefined, but it can't be undefined, so the derivative must equal 0. Done. All right, so there was case number 1. So case number 2, this is crazy fast. Now that we've talked about this, this is now going to be where there's a point that's below these endpoints. All right, well, ready? Here's your proof. It's a continuous function, so we're guaranteed extreme values. The absolute min can't be at an endpoint, because now these two, there are points that are lower than it. Well, this critical point must have the derivative equal 0 since it's differentiable. Case 2 is pretty much case 1. It's just changed the direction of an inequality. So those two are about the same. Now, the third case, this one's actually the easy one. So here's case number 3. Case number 3, this is that f of x equals f of a for all x. Where we never have a point that's higher or a point that's lower. Okay, well, think about what that looks like in a picture. We're just going to go ahead and connect those two dots with the horizontal line. What's the proof for this one? What statement am I going to write to show you that there is a C where the derivative equals 0? And don't overthink it. What kind of function is this? Good, Bailey. It's a constant function. What's the derivative of a constant?
0.
Done. Right? So in this case, here's my write-up. F of x is constant. Therefore, f prime of x equals 0 for all x, which means that there is a point where it equals 0 all of the points. Okay, so there's Rolle's theorem. Yay. So if you're ever in a situation where you've got a continuous differentiable function whose endpoints have the same value, you're guaranteed to have the derivative equal 0 somewhere in there. Okay, that's a lot of ifs. And honestly, Rolle's theorem, we don't care about it on its own. Never use it on its own. But where we are going to use it is to prove the next theorem, which is called the mean value theorem. But we'll save that for Wednesday. Okay. Because it looks like we're out of time. Oh man, just about perfect. So just so you know what's coming up on Wednesday, we're going to look at the mean value theorem. That'll be our next theorem. And then we'll use that to help us go forward. And where we're going to go with our going forward is analyzing functions, looking at them, figuring out where maxes and mins are, where they're going up, where they're going down, how they're curved, and all this. And so we're basically going to be using derivatives for the rest of this week to get really, really good graphs of functions, to analyze functions, so we'll know everything about them just using calculus. So that's the plan. That's where we're going. So exams, I haven't graded them yet because there's still a couple people that need to wrap them up, but I should have them Wednesday. The other thing I want to mention is that I'm not going to have office hours tomorrow. I'm actually going to be volunteering as a poll watcher, make sure no shenanigans are going on during this election. So I'm going to be away from the computer. But I will definitely be back for office hours on Wednesday. All right. So with that, have an awesome couple of days. Don't forget, homework is due tonight by midnight. And I will see you all on Wednesday.